This is an intro to the Bode plot of a transfer function, g of s, which is often taken to be the open loop transfer function from summer to summer. In other words, what's going to happen to the system when I close the loop on it is answered by the open loop Bode plot. So if I let s equals j omega and plot the resulting magnitude of g versus omega on a Bode plot, which has frequency on a log scale, and I plot the magnitude in powers of 10, which also is equivalent to a log scale, where we note that 20 times log to the base 10 of the magnitude of g is equal to g in decibels. So this turns out to be each power of 10 on g being 20 decibels every time I have an increase in power of 10. So 40 dB would correspond to 10 squared in magnitude. So you can have this Y scale either in 20 dB increments or in powers of 10. That's equivalent. And you can have this scale on here in radians or in hertz. But they're both essentially log scales. And why the Bode plot is so important, why it's so important, is that it shows you, it gives you the distribution of energy in the impulse response. If you put some impulse, or if you put some energy into the system, how is that energy going to be distributed with frequency? Where is the frequency? Where is the energy going to be greatest? Where is it going to be least? And how is it going to be? Now this allows us to design the Bode plot in segments. We can design a mid-segment for the Bode plot, just do our design in that frequency range, or we can design perhaps in low frequency range, just over here. And the Bode plot allows us to apply the principles to each segment individually, making the design process for control much simpler. But let's look more fundamentally what a Bode plot is. If I take my input as a sine, and we're going to call the frequency omega d, using the control symbology, then my output coming out of y is also going to be in the steady state. The steady state output is going to be a sinusoid as well. But the sinusoid in the steady state, although it will be at the same frequency, will have a different magnitude than u. And the ratio of that magnitude as frequency changes, or 20 log of that magnitude, is what we're going to plot on the Bode plot. And one of the key things of extreme importance is when the Bode plot crosses what we call 0 dB. Now 0 dB, since dBs are the log, that means that the output equals the input. I have a log of 1, is 0. So the output equals the input right at the crossover frequency, and that turns out to be a crucial point for us to exist, or to analyze. Because if we have the phase curve, if we also have the phase curve, like so, and at the crossover frequency, it's very important that we not be 180 degrees out of phase. Think about that. If I have a closed loop system, and in that system, if the output is out of phase with the input as it comes back, if it's out of phase with the input, that negative side is going to put it back into phase, and if it has a value larger than the input value was, then obviously I'm going to be unstable in that loop. That loop is going to generate a larger and larger number. Well, that's kind of what the crossover frequency tells us. If we go down to the crossover frequency, which is where the output equals the input, then we can see if our output is out of phase with the input. So it'll be out of phase with the input at 100 at minus 180. If I'm not there yet, then the system has some stability. It has some stability. The phase margin is the amount of phase angle in degrees at which I'm not at 180 degrees. Now don't let the sign convention fool you. If this distance that as I'm showing it here is positive, that distance is positive, then you have a positive phase margin. You're not at 180 degrees yet. So you have a positive phase margin. If, on the other hand, you have crossed. If your phase curve has done this, and you've passed the 180 degrees mark, then you have a negative phase margin, and that would be unstable. Equivalently, you could look at a concept called the gain margin. And in the gain margin, I'm going to come to the 180 degree frequency point. So here's a frequency where I have minus 180. And now I'm going to go up here, and I'm going to see that, oh, my output is less than my input. It's less than my input by so much, so many dB. And if I'm less than the 0 dB line, then that means that when the output gets fed back, it's going to be less than it was at the input. And so it might oscillate a little bit, but it's not going to be unstable. So this is a positive gain margin, and it's shown over here by size of tool in MATLAB. And the phase margin, of course, is shown in the phase curve. Now the phase margin is considered a robustness measure to show you how much slop you can have in the system with unmodeled dynamics or with what's called phase delay. So if you have unmodeled system dynamics, then you want your control system to still be stable. And that's why almost every specification is going to have a phase margin specification on the primary control loop. Usually it's around 45 to 60 degrees. And if you have a gain margin specification, when omega is equal to 180, that's normally around 6 dB. 6 dB is a factor of 2. 6 dB corresponds to a factor of 2. The 20 log magnitude of 2 is 6 dB. So the square root of 2 would be 3 dB. Now the other critical metric, other than phase margin and gain margin, is the closed loop bandwidth. Now the closed loop bandwidth is predicted by the open loop crossover. So in other words, the bandwidth, which is a property of the closed loop transfer function, that's not shown here. The closed loop bandwidth corresponds closely, within 20 or 30% usually, it corresponds to the open loop crossover. So if the open loop crossover frequency goes up, the closed loop bandwidth goes up. If it goes down, the closed loop bandwidth goes down. They travel together, off by a slight factor, but they travel together. Now if we were to look at the closed loop Bode plot, this is the closed loop transfer function, we see that all good closed loop transfer functions look the same. They all are at 0 dB out to a certain frequency, then maybe a little resonance, and then they'll start falling off. And when they go down 3 dB, that's normally the frequency that you'd call your bandwidth, right there at 3 dB. Usually that corresponds to like a 90 degrees of phase loss in the phase curve. This happens when you have pure resonance. If you have a resonant circuit, for example, then this is what you'll notice. You'll have a 3 dB drop after resonance and a 90 degree phase loss. That's considered the bandwidth of the system. Now we don't normally design to these bandwidths because all closed loop systems look the same. They all look the same. So we don't have a real idea of how to fix a system by looking at the closed loop transfer function. On the other hand, we do know how to fix a system to make it look good in the closed loop using the open loop transfer function. In other words, if you give me an open loop transfer function that looks like this, we will know at the end of this course how to fix that transfer function to give yourself a good closed loop transfer function. And if you have an open loop transfer function whose phase looks like this, and again, we'll see how to make that open loop system different so that the closed loop transfer function looks good, gives us a good bandwidth. Almost all system specifications, almost all specs, are specs on closed loop bandwidth. In other words, you could consider this money. The more bandwidth you want out of the system, the more fuel you're going to use, the more money you're going to spend, and the more precise that system is going to be. We don't ever want to make the bandwidth larger than it needs to be to do a job because of that. So our bandwidth spec is a key specification, and we would always question when this spec is set to make sure that it is set no bigger than it needs to be because of the cost involved and the complexity of the control system design that's required. So, given the open loop transfer function, we have our crossover frequency that's going to be our predictor of a bandwidth. In other words, our bandwidth is going to be predicted by the crossover frequency. And we're going to design our system so that we have a net resulting phase margin, and that phase margin is going to guarantee us against unmodeled dynamics, different system characteristics, and errors and inaccuracies in our model parameters.